Good morning. All right, so 2.2, derivative as a function. Define the derivative of a function. Graph the derivative of a function and identify where a function has no derivative. Now, first, when we do a derivative at a point, what does that give me? Slope. We get slope. Slope. All these times, derivative, we're trying to find the slope, right? Yes. So the slope of the what? The tangent line. Remember? Because we're not dealing with straight lines here, we're dealing with curves. So I'm looking for the slope at a point. Okay, slope at a point. That's the rate of change. The rate of change, that is slope formula. Delta y over delta x. So it's my change in height over my change in width. Oh, wait, hold on. Okay, you didn't see that. Find the derivative of the function here. Any real number c. So as this approaches c, okay, so what would I do here? Okay, so that would be what? C plus h squared minus 5c plus h minus the whole thing, x squared minus 5x. G is not here. All over h. So, for this right here, as I go through and do this, actually, sorry, you're right. Okay, there's x's where it's not, shouldn't be x's. This should be c's, right? This should be c squared minus 5c. There we go, sorry. I know something looked odd. All right, square this one right here. I'm gonna have c squared plus 2ch plus h squared minus 5c minus 5h minus c squared plus 5c. Now, when I do this, something happens every time. What do you think that happens? Go ahead, take a guess. Something does what? Cancels. Something cancels. So I have my minus 5c, I have my plus 5c, minus c squared, minus c squared. So I'm left with, okay, so h squared, right? H squared plus 2ch minus 5h all over h. What does my top have in common? What does it? They all have a common factor of h, right? So we're going to F that right now. So after I take that out, I'm going to have h plus 2c minus 5 all over h. And when I cancel out that h, those go away, right? Yes. And now we're taking the limit as h approaches c. So this one's going to be as h approaches 0 here for this. Now, the definition of the derivative says we're taking it as the limit h approaches 0. And so now, plug in 0 for my h. 0 for the h. If it's 0 for the h, right? What's my derivative going to be? What happens to the h? It always goes to 0. As the distance in between here and here goes to 0, it's always like that. So as I take this limit, this goes away. So it would be 2c minus 5. That is the equation for the tangent right there. So when I want to actually find the slope at any number c, it's going to look like that. So when I find this one right here, and I say, hey, let's find it at 2. So now at 2, it would be 2 times 2 is 4, minus 5 is negative 1. My slope of this would be negative 1 there, because I'm always taking the limit according to C. So now this is also the same thing as saying my, let me see, y2 minus y1 over x2 minus x1. So if I am looking at a little graph right here, and I'm going this way, and I call this one is going to be my x, and it's going this way to some value, as it's going to C over here, as it approaches C. This one right here, this one's going to be C comma f of x plus C. No, this one's x plus C also. X plus C. And this one right here, this point is going to be my x comma f of x. So it's the slope formula out of this all the time. So it's my y2, so there's my f of x plus c minus f of x over, it's going to be x plus c minus my initial value, which is x. So as I do this, as I'm trying to find the slope going from here to here, from whichever arbitrary line that I'm making, because I'm asking to see the distance in between my delta x right here, my delta x, as my delta x goes to 0. So I'm trying to push these things so close together that the distance in between these 2 points are going to be 0. So I'm going from a secant line, which I have 2 endpoints, and I'm actually finding the slope in between them. I'm trying to find it where it's eventually getting to 0. Okay, the distance separating this one here and this one here to be 0. So as I'm doing that, that's why, so I can clean this up now, right? So if I clean that up, now it's going to be f of x plus c minus f of x over c. So this is, when we do this, we're taking the limit as, for this one right here, x approaches c, where I'm trying to get it to be 0. The distance in between here and here to be 0. So it's always going to end up, as this approaches c, where I want 0. If you notice, I can't just plug in here, right? For all my problems that I was doing last time, I can't just plug in 0, because that will give me 0 in the denominator. So I have to factor all this out. That's the same thing as what we just did right there. Okay, this time they actually, instead of saying x, they said h and c. They just gave you something different there. Maybe? No? Possibly. All right? Just nod our head and agree. Okay. All right, you didn't see that. Okay. Find the derivative function, determine the domain. Now, let's start off with, to do the derivative, so using the process, so it's going to be, let me see, x plus c, and this is to the 1/2, minus x to the 1/2. I like writing my square roots as a exponent, because it makes so much easier when we're actually taking derivatives and not looking it up on our phone, but it's all right. Now, over, okay, so this one's just going to be c, right? So it's a limit as x approaches 0, or for my c approaches 0 here. For this one right here, to find this limit, as I do this, I'm going to come up with an equation out of this. So let's see. So for right here, when I do this, it's going to give me, let's see, right here, I'm going to have to difference of, yeah, difference of squares. Crap, I forgot this one. I'm so used to doing. All right, yeah. Okay, so yeah, so it is the conjugate, so I don't forget that one. All right, so it's going to be x plus c 1/2 plus x to the 1/2. So x plus c to the 1/2 plus x to the 1/2. See this right here? There is, I would do difference of squares, because I can make that into a perfect square because I have exponent, exponent, and I have a minus sign in between. But if I did that, if I factor it out, it's going to get me to the 4th power, wouldn't it? Yeah? Because square is 4th power times 4th power, isn't it? Yeah. So I don't want to do that. I don't want to get into deeper radicals. I want to try and get rid of my radicals. When I do that, I'm going to multiply by the conjugate here. And the conjugate is going to be the difference of this. So when I actually do my foiling here, when I FOIL all this up here, this is going to end up becoming, you know, like this x to the 1/2 times x to 1/2 is going to give me x to the 1, right? So it's going to do some canceling for me, and that's what I need to do. Because I have a radical there, I have to try and get rid of the radical. So I was either going to do this or try to do some weird, you know, squaring type thing. But the conjugate here is helpful because I have binomial here, so I could actually multiply by the conjugate on this one. So if I go through and actually do my distribution, there times there is just going to give me x plus c, right? Yes? Yes. 1/2 times 1/2 gives me just 1, right? All right, so now keep going over here. So it's going to be plus x 1/2 times x plus c to the 1/2. Next one's going to be minus x 1/2 times x plus c to the 1/2, right? And over here, this is going to give me minus x to the 1st, right? And on the bottom, I'm going to leave that factored. So it's going to be c quantity x plus c 1/2 plus x to the 1/2. There we go. All right, so now my middle terms right here, those go away, don't they? All those go away because I have a plus x to the 1/2, x plus c 1/2, and a minus also. So that's going to go away. So it's going to give me x plus c minus x, right? All over my messed up denominator. C. Yeah. So on this one right here, the x's are going to go away. So that's going to be nice. That's going to go away. So that's going to leave me what on top? C. And what do I still have factored out front? C. I have a C on top and a C on bottom. So the x's go away, but the c's will cancel now, won't they? So what's that going to leave me on top?
1.
1. So I'm going to have 1 over x plus c plus x 1/2. Okay. So now we could take this as c goes 0. Guess what? All the c's are gone now, aren't they? So I'm left with just this. So now I have the derivative. So this is my f prime of x. Now, what is the domain of f prime of x? What's it first? What's the domain of my function, f of x? Think about it. What cannot? It can't be negative, can it? It could be 0 though, right?
Yeah.
It can be 0, but it can't be negative. So numbers greater than equal to 0, okay? So now determine the domain of f prime. Okay, so again, can it be negative? No, it can't be negative. Now, if there was a minus sign right here, if there was a minus sign right here, that would give me another restriction, right?
Yes.
Am I allowed to have 0 in the denominator?
No.
No. But since I have a plus sign right here, that's not going to be a problem. Okay, it's not going to be a problem. So I could actually, if I really need to figure it out, I could just go, hey, set all that equal to 0 and see what I get. Okay? So, now, let's do the c to 0. So it's going to be 1 over, so if c goes to 0, it's x to the 1/2 plus x to the 1/2, which is going to give me x to the 2, x, I'm sorry, 1 over 2 x to the 1/2. There we go. Because as we plugged in 0 for c, that goes away, and so then I did my right here, and I combine like terms. Yes, no, maybe?
Yes.
Yes.
Okay, good. So,
Can you explain me why c goes to 0?
okay, remember what I was saying? What I was saying, the limit as, you know, c goes to 0. So, as c goes to 0, going back here. So, we're going from this, which is a secant line. It has 2 endpoints, right? I don't want a secant line. I want a line, I want the line at that point. So I have to get this to here, this delta x, to be 0. So the difference, so right here, so it's as x goes to 0. Okay? So the limit from this to this, instead of going to c, so it's x plus 0, right? So x plus, so as c goes to 0, because over here I have x plus c, right?
Okay.
So if I'm plugging in 0 here, that means I'm on top of x here, right? So if I have 1 here, so I have x plus 1, so that's really not the same point, is it?
Yeah.
That's 2 separate points. So I'm going to have an x and I'm going to have an x plus 1. But over here, when I get this down to 0, that's where I'm finding the slope of the tangent at a single point. Because I'm using a limit process to get this to 0.
Okay, it's clear.
Okay?
Yeah.
Alright, so does that make a little bit more sense? Whenever I'm trying to do this, I'm using the limit process here. I'm using limit process. I'm always taking this to 0. Always take the c to 0. We're always taking the c to 0 because I want this to be 0. I want there to be no distance in between my x and my c value. If there's no distance there, that means that my 2 points that are eventually getting smaller and smaller and smaller and smaller, I finally get to where they're on top of each other, and I get that the slope is at that point. At that point right there, just the single x value. Not 2 separate x values, just a single x value. And that's what I'm trying to get. I'm trying to get it to be squashed down to just be 1 point. That's why I'm always taking the c to 0, and then I'm left with the derivative of my function at that. You guys will like me so much more once we actually get to the next section. Remember the voodoo magic I showed you the other day? It's all voodoo magic next time. Yes?
Do we have to do that if we know how to find the derivative like right away without all of that? Like, can I just...
Right now, yes. For this one, there is a process for it because
I know,
on the
but
exams,
on the test, do I need to know how to do it like that way?
no.
Oh, it's okay.
This
I just
test,
do it right away.
yeah, this test, you'll be fine without it. Yes.
So there's an easier way out.
Yes.
Okay.
This is an algebra way to do this.
You scared me.
Because the limit process, this is algebra. It's all algebra. I gave you an equation, you plug in points. It's algebra. Okay, the voodoo magic comes in next, the next section.
Let's get to it.
That's when we get the Leibniz.
I know.
All right, so yes, Gottfried Leibniz. Yes. All right, so surface area S in square meters of a balloon expanding as a function of time in seconds according to S, and S of t equals 5t squared. Find the rate of change of the surface area of the balloon with respect to time. All right, so we have, so let's do the whole thing again. So let's hope you paid attention. So I'm taking the limit as c goes to 0, right? So the limit process is going to be 5, and it's going to be so it's usually x plus c, right? So this is t plus c squared, right? Minus 5, yeah, 5t squared. There we go. I was trying to do a 5 and mess it up. 5t squared all over c. Right? Because you guys see, you know, when I showed you the variables went away. Remember we had those x's on the last one? They went away. These ones are in terms of t.
So now you both have an opposite.
So right here. So if you notice the x's here went away whenever I did this, and I came up with the same function, but this time I'm actually using t's. All right, so now I have to expand it. I have to expand this, so it's going to be 5 parentheses t squared plus 2tc plus c squared minus 5t squared all over c. All right, I'm hoping you guys are seeing the pattern on the squaring a binomial. It's the first one squared, it's the last one squared, and in the middle it's going to be first, last, times 2. This times 2. So it's 2tc. It's a pattern all the time. So I don't know if you guys had that in your other class, but yeah. All right, do my distribution. So it's going to be 5t squared plus 10tc plus 5c squared. 5c squared minus 5t all over c. Now, what goes away? 5t squared. And that goes away, so I'm going to be left with, so let's see, equals 5c squared plus 10c all over c. Factor out that c, right? Okay, do I need to make it in 2 steps? I can factor out 1c, right? And then cancel it. So I'm going to be left with 5c plus 10. Okay.
And then you solve for C.
10t, you're right, 10t. 10t. And then do the limit as c approaches 0. So this is going to be, so s prime of t is going to be what? 10t. No, because no one's ever going to want to do the real way.
Yeah,
So
that-
I know it works, but
Why?
okay. Because this is algebra and it's important. It's stuff that you have to do. You can't go straight to the voodoo because there's a lot of types of questions that you have to know how to do the algebra on it. Ah, you didn't see this. Okay. Find f prime if f of x is equal to x cubed minus 1. All right, so I already have it here for you. Now, I want to take a look at my previous one. Was it 5t squared, right? So if I start off with s and s prime was 10t. What can I say looking at my function and then my derivative?
The degree becomes less.
The degree is less, isn't it? Okay, so how much is the degree less? Okay, so x squared minus 5x. So if I had and the derivative here's another one of what we already did. What happened?
The degree less.
The degree is one less each time, right? For every term, the degree is one less. So, you guys ready? You guys ready? Okay, so I need you guys to warm up on this one, all right? Okay, so you guys get your arms ready. Okay, do a couple sine waves. Come on, sine waves here. You know you want to, right?
What if that's what people just like call them?
Huh? Sine waves. Okay, so now, are you ready? So, help me out. X squared, what does it look like? Get those hands. Yes, x squared, right? Ah, okay, so now, you ready? Negative x squared. Ooh. All right. So, positive x cubed. Everyone going the right way, right? Okay, yes, positive x cubed. All right, so now, x to the fourth.
No, it's,
Oh, yeah,
it's
'cause
closer.
It's both up, right? So what could I say? So all even numbers should be ending in the same place, right? So even numbers, so if I have an x to the fourth, both should go up. If I have an x to the fifth, I should have one up and one down, right? Okay, that's very good in understanding. So on my function over here, I started off with the x cubed, didn't I? So that was a cube, so we did a little thing right here, so then we took away 1, so then my x squared had to be both up, didn't it? So, now, I'm going to use this as example. You know, we just did the math enough times, so I'm going to show you guys something, and hopefully this will help. Okay. Now, think about this by mentally drawing little tangent lines. Little tangent lines. What's the slope of the line right here? Slope. We read from left to right. The slope of the line, it's positive, isn't it? Okay, that's a positive number, isn't it? Okay, so it is positive. It is going up, isn't it? So now we're looking at the derivative at the same point right here. Is that a positive number? Yes, yes it is.
Oh, okay.
Yeah, it's a positive number. It's right in here, isn't it?
Yeah.
Huh? No. It doesn't matter. We're talking about the first derivative. If we were talking about the second derivative, that would be my acceleration. And I would be talking about, okay, so the slope of my derivative of velocity would be going down. So that means my acceleration would be going down. But I'm still increasing in speed, right? So if I'm driving in a car, okay, driving a car, velocity is my speed. Acceleration, okay, it's either increasing or decreasing. So what he just asked right there, so this slope is going up, isn't it? So that means that I am still going forward, aren't I? So my speed is still going forward, it's still positive, right? So I have a positive speed here, right? But my velocity, what do you think my velocity is doing? It's going down. So that means I'm slowing down, but I'm still going forward, aren't I? That's what we're looking at, okay? So, but forget the velocity part for right now. We're just talking about the numbers. So if I'm talking about the numbers, so, okay, I got time. All right, so now right here, what's the slope of that line? 0. So according to my function right here, there, the slope is 0. So this one right here is not what you think. This is actually the slopes at that point. So here the slope is at -2, the slope should be up here, right? Whatever that is. So at 0, the slope is 0, right? Okay, so at 1, right here, at 1, what should my slope be? Okay, my slope, okay, so if you notice, at 1 it's going up, isn't it? It's going up, so my slope is right here, so it should be positive, right? It's going up. So the slope right there, it's positive, it's going up, isn't it? Way over here, isn't the slope going up really fast? So these slopes are a lot bigger than these slopes down here. That's why my line, my green line, is still up here. Is there any place on the function line that it is going down? Is there any place on my function, this blue line, that it's going down? No. So there's no place that my slope is negative, is it? Does that make sense?
Yeah.
Okay, good. All right, don't forget, like and subscribe. Today is a travel day.